Thank you. Yeah, so today in my talk, I have got quite a few demos, so I hope I have made sufficient sacrifices to the demo gods and that we'll be lucky today. So Matthias ahead of me, I don't know how many of you were here in this room for the talk immediately preceding me, but he did a great job of talking a bit about eBPF for observability. I'm going to talk a bit about eBPF for security. So yeah, I work at Isovalent, which is the creator of the Cilium project, which is now part of CNCF. Again, Matthias did a great job showing us some Cilium demo in the previous talk, so massive thanks for that. How many of you here have heard of eBPF before? Quite a few hands, good. How many of you have used Cilium? Any Cilium users? Excellent, thank you, brilliant. So yeah, Cilium is really all about networking, and I'm going to talk about security. But as you'll see, there's a lot of commonality in eBPF. And I've been interested in security for quite a while. I wrote a book about container security. I've also recently written a short book about eBPF. We're giving away copies on the Isovalent booth, and I'll be doing a signing, I think, after lunch, so come along and get your copies of those. But the real reason why I'm showing this is because this talk is bringing together two of my really big interests, security and eBPF. So what even do I mean when I say eBPF? The acronym stands for Extended Berkeley Packet Filter, but honestly, just forget that, because it's so much more than packet filtering now. What eBPF lets you do is run custom programs in the kernel. We can customize the way the kernel behaves dynamically. Let's just make sure that we're all on the same page about what I mean when I say the kernel. So as application developers, we're usually writing in user space. But whenever our user space code wants to do anything that interacts with hardware, and that means accessing files, communicating over a network, writing anything to a screen, even accessing memory, all of these things require some interaction with hardware, and it's the kernel that provides that interface to hardware-related activities. So whenever our user space applications want to do any of those things, they have to make calls over what's called the system call interface and ask the kernel for help doing those things. The kernel's also coordinating all of the different processes that are running at any given time. So with eBPF, we can attach programs to different events in the kernel. And those events can relate to any function call in the kernel. They can relate to network packets arriving. They can relate to all manner of different things across a running system. So we can use eBPF to detect and react to events occurring in the kernel. So I'm going to show a little hello world example. And is that big enough? Can you all see it okay? Yep, I can see some thumbs up, so good. Let's change this to say, hello, ContainerDays. And if I run this, now let's run it in a shell here. Hello world, hopefully. No, it's hello.py, isn't it? And if I do some things, we see some tracing. Hooray, it works. We can also see some contextual information. So if I run PS, we can see the process ID was 3560, and that's part of what's been traced out here in my output from my eBPF program. And that's quite important. The eBPF programs get triggered by events, and there's some contextual information about that event that we can use. If it was a network packet arriving that triggered the eBPF program, the packet would be the context. If it's related to something like this, where I'm looking at a system call, the context will have information about the process that triggered that event. So eBPF has been used quite a lot over the last few years to create observability tools that we can load dynamically into the kernel to trace what's happening. We saw some examples of this in the previous talk. And the way these are implemented, there'll be some user space application that you run that does some tracing. It loads an eBPF program into the kernel. It also loads what we call a map. And a map is a data structure that we can share between eBPF programs and user space. So our program reacts to an event and maybe gathers some metrics. Those metrics get stored in the map, and then our user space program can asynchronously come and read that information out of the map and use that to show some metrics, some information about the events that have been happening that we're interested in. And as I said, there's a whole ton of these that have been built and used over the years. This is a picture from the BCC project. And I think it's quite a scary picture, really. I mean, I don't expect you to read all the words, but the point of it is there are tools that have been developed to collect information about every aspect of a running system. So there are tools here that relate to network functionality, file functionality, CPU performance, memory, everything. There's probably some tool in the BCC project that you can use to gather information about that aspect of the system. I'm going to use OpenSnoop as an example, and wonder which machine I'm going to do that on. I think I'm going to do it on this machine. So OpenSnoop snoops on file opens, and if I, let's say, hello. OK, so there's lots of stuff going on that's opening files already. But if I write something to a file called ContainerDays, we should see that before it scrolls off the screen. There it is. So again, we got contextual information using eBPF to tell us what process wrote a file or accessed a file, actually opened a file. OK. So that's just an example of one of many, many observability tools that have been built using eBPF. Now let's think a bit about how this works in a containerized environment like Kubernetes. However many containers we have, there is only one kernel per virtual machine or bare metal machine. So we have our user space applications running in pods. They're in containers inside pods. And however many pods are running on a given machine, on a given Kubernetes node, they all share one kernel. So whenever those applications do any interesting activities, or whenever Kubernetes creates new containers, all of these things will require assistance from the kernel. The kernel knows about everything that's happening in all of those applications. So if we use eBPF to instrument the kernel, we can get visibility into what's happening in all of our user space applications. And we didn't have to change anything about those applications. When I've run things like PS in a terminal, I didn't have to change anything about my bash terminal. I didn't have to change anything about the PS executable. It was all already visible to eBPF. And the same is true of your applications. If they're running on a machine, eBPF can instrument that machine and see what those applications are doing. The fact that you don't have to make any configuration changes, that you can get visibility into processes that are already running, is hugely useful for observability in general and security in particular. One thing we haven't seen in the examples so far is any way of tying information to containerized identities. If you've got a Kubernetes cluster with hundreds, thousands of pods, you want to be able to relate activity to the Kubernetes identities, to those pods. There are a few tools that can give you those relations. I'm going to show an example of a tool called Inspector Gadget. So here I have a cluster with a few pods. Let's just, yeah. And if I do gadget trace open, this is very much inspired by that OpenSnoop example that I showed you. This is Inspector Gadget monitoring file opens. So if I exec into one of those pods, I can exec into my X-Wing fighter, and the act of starting the shell has caused a number of different files to be opened. But just to be explicit, let's look at the password file from inside this pod, and you can see that's visible to the eBPF tooling, and it's been associated with the Kubernetes identity where that activity has taken place. So, okay. That's just one example of eBPF tooling that is aware of Kubernetes identities. This is another example, a CNCF project called Pixie. Pixie enables you to run lots of different types of eBPF-based observability tooling on your cluster. This is just one example of the kind of outputs it can give you. This is a flame graph of CPU usage across the entire cluster, aggregated across the entire cluster. So tools like this can be really useful for aggregating data. And another example, this is again, something you might have seen an example of in the previous talk, the Hubble component of Cilium, which can show you how network flows are, or how network packets are flowing within your cluster, how Kubernetes services are communicating with each other, and metrics like latency or number of packet drops, or you name it, you can collect the metrics. So what I've talked about so far is eBPF's ability to let you observe things about your applications, whether they're running in Kubernetes or elsewhere. But we really want to talk about security. How can we use that observability information for security purposes? I think observability is an inherent part of security. You can't prevent something that you can't observe. You have to be able to see something happening before you can prevent it. What is the difference between observability and security observability? The difference really is policy, being able to decide which of the activity that you can observe, when is it malicious? How do we tell the difference between normal expected behavior and malicious behavior or suspicious behavior? And the answer is policy. If you've detected something that looks like a suspicious event, the person who's going to handle that incident really wants to understand not just that something bad has happened, but they also want to understand how it happened, what was the root cause, which of your applications, which of your pods, which of your nodes are affected. And in order to find that out, you're going to need contextual information. We've already seen that eBPF can provide you contextual information, and lots of work has been done in various projects to map that context to Kubernetes identities. So eBPF is a really powerful way of collecting that data and mapping it to the contextual information. And the kind of activity that we care about for security, runtime security in particular, is all the kind of things that interact with hardware. We care about file access. We care about, is this particular application allowed to write to that file? Is this application making network requests that we expect? Or is it connecting to some cryptocurrency mining pool, which would be suspicious? pretty much everything that we want to detect from a runtime security perspective relates to hardware access. It relates to things that the kernel's going to do for us. Executing new programs. Should a particular executable be permitted? Well, eBPF is in a great position to spot that. We can detect what programs are being executed when the kernel starts them. There have been quite a few security tools already built using eBPF. And perhaps the sort of obvious way to detect these kind of security events was to instrument system calls. So we talked about how user space applications have to make system calls to the kernel. So isn't that a great thing to observe so we can see whether user space applications are doing suspicious things? The problem is that there is a time of check to time of use vulnerability if you look at the system call interface. And in fact, it's documented in the kernel that you really shouldn't use the system call interface for security purposes, because what happens is your user space application passes some arguments in that system call, and they have to be copied into the kernel's memory space. The kernel will build up a data structure about the file you're about to open or the process you're about to execute. And if we look at those arguments too soon, if we look at them at the entry to the system call, they haven't been copied into the kernel yet, and there is a window of opportunity for an attacker to change those parameters before the kernel does what it's going to do. And this is actually a pretty well-known kind of concern. There were some really great talks last year about how this affects some of the eBPF-based security tools, things like Falco. So while observing system calls is fine for getting a general idea of what is happening on your system, it's not the most appropriate interface to use for serious runtime security tooling because of these vulnerabilities. What we need to do is make these checks with eBPF later. We need to make those checks after the arguments have been copied into the kernel. If we can look at the kernel's data structure, then we know exactly what file is about to be opened, or we know exactly what data the kernel has about whatever operation it is we're going to perform. And there is a really great interface for doing this. It's called the Linux Security Module interface. One of the reasons why people use system calls is because it's a stable interface. It's guaranteed not to change from one kernel release to the next. And the same is true of this Linux Security Module interface. It's a stable interface, and it was provided originally for security kernel modules. You might have used things like AppArmor. SE Linux also uses the LSM API. So it gives hooks at the right point for checking parameters before the kernel does something like allowing file access, for example. Makes a lot of sense that we could hook eBPF programs to those hooks, to those function calls on the LSM interface. And that gives us the benefit of using the stable API, the stable API, it being safe places to make proper security checks. But has anybody here used AppArmor or SE Linux before? Few of you. Keep your hands up if you thought that was really fun and enjoyable and easy to use. Yeah, maybe, yeah, I think, yeah. No, it's not. And it's even more complicated in a containerized environment. So being able to use eBPF, where we can change policies, we can change tooling dynamically, we can protect existing applications without having to change them, but we can run sort of bespoke policies, and we can tailor those policies to individual containers on the fly. So BPF LSM is a really sensible way of using eBPF for security tooling. I have a little example here, if I can find the right machine. Yeah, so in this example, I've actually got two eBPF programs. One that's just going to trace out the fact that I'm making a chmod system call. I'm going to change the permissions on a file. And then I've got an LSM hook here. This is actually attached to the function in the kernel where everything is ready set up to tell us we're about to change the mode of this file. And in this second case, in the LSM interface, I can get hold of the file name that we're about to change. This is going to output to a kernel trace pipe. So yeah, just run this, and hopefully we should see just create a file, and then if I change the mode of that file, we see both of those tracing output, and we can see the name of the file was included. We couldn't reliably get that in the system call interface. So this LSM set of hooks is great, but you need a kernel that is pretty recent. 5.7 is where this BPF LSM capability was added. And you also kind of want to hook that up to the Kubernetes contextual information, like we saw with some of the other tooling. The fact that this needs kernel 5.7 does mean that it's probably not available for a lot of production users. People are pretty conservative about the kernel versions they're running in production. So some of my very smart colleagues who know lots about the kernel and who are, in fact, kernel developers, looked at this and were like, well, the LSM API gives us this stable interface. It's declared stable. But there are loads of other functions in the kernel that, and we can attach eBPF to any function in the kernel, and loads of them haven't changed for a long time, and there's no particular plan to change them. There's no guarantee that they won't change, but we know that they haven't changed and are unlikely to change. Why not hook into those functions, which we can do in older kernel versions? We don't need that BPF capability to be added. So we can hook into function calls that are roughly the equivalent kind of places to where LSM API hooks in, but just using the regular kprobe approach. And we have a sub-project in Tetragon that does exactly that. So it's hooking into these function calls that are safe and sufficiently stable, if not guaranteed to be stable. We get all the benefits of being able to create policy dynamically, to attach and protect pre-existing processes. And because it's part of Cilium, we've used this ability to kind of combine the contextual information with Kubernetes identities. It's called Tetragon after this bee. You might have noticed the eBPF logo is a bee. There's a lot of bees around in the eBPF world. This particular bee is, it builds small, unobtrusive nests, according to Wikipedia, and it produces large amounts of honey, and it's generally considered safe for humans. So that seems like quite a nice analogy for a security tool that's going to produce a lot of really useful security information in a very lightweight way, and hopefully without harm. The policies that we have in Tetragon, I will say, are pretty kind of low level. So they're requiring knowledge of things like fd install is the name of that function that we're going to attach to. But there are tons of examples. The example I'm going to show you, we're going to be interested in files that live in the /etc directory. We're going to follow reads and writes and opens and closes on any file in that directory. One of the interesting things about Tetragon is we can do this filtering in the kernel. So we're not generating events for every single file and then filtering it in user space. We're doing the filtering in the kernel. So let's find my cluster again, and don't know if I've got any tracing policies already applied. OK, I do. I have that policy I just showed you applied. So if here's my Tetragon output. I'll just show you very quickly that Tetragon creates a ton of really detailed log information, and it's deployed as a daemon set, so there's a Tetragon agent on every node that loads an eBPF or a set of eBPF programs into every node. But because that's pretty hard to read, we have a nice tool. Oh, what's happened to my screen? Demo gods, come on. I'm going to just see if connecting and reconnecting will bring it back. Oh, OK, we're there. Nobody breathe. OK, so I've piped that log output into the Tetragon observe command, which makes things much easier to read. And we can see, actually, the previous events that had occurred, for example, when I was editing etc password earlier. So let's just do that again. And you can see there's vi opened and then closed the etc password file. And just for fun, let's add some kind of extra line here. Now, normally, you really don't want people messing with password files. That doesn't seem like a great idea. So seeing things like a write event to a file in the etc directory could be considered a security relevant event. You might want to send that to some kind of security logging system and alert people about that. And get information about things like how many bytes were written and so on. So we can get this useful security observability information with Tetragon. We could combine that also with networking information from Cilium. So I showed you Hubble earlier. This is like a kind of combination of Hubble data and Tetragon runtime execution data, where you'd be able to see if there was a malicious-looking network connection, like to this funny-looking not reverse shell address. What was the pod that was involved? What was the executable? When did it happen? What was the process execution tree that caused that network connection? That would be super useful forensics for figuring out how the pod got compromised, what had gone wrong, how did this happen? But what if we wanted to not just detect that these things happened, but actually prevent them? And we already have examples, and have had for some years, examples of runtime policy enforced by eBPF in the form of network policies. If you have a network policy, it has to act in real time. It's looking at network packets, deciding whether they do or don't meet policy, and it just drops them if they're out of policy. This is a screenshot from networkpolicy.io. There's a policy editor there that you can use to see how policies would affect flows between different pods and services in your cluster. So we can do it for network policies. What about runtime policies? Could we say, I want to stop people from editing files in the etc. directory, for example. Traditionally, this has been done by detecting the events in the kernel, sending them to user space, having user space go, yeah, don't like the look of that, I'm going to kill the process that's responsible. The problem with that is there is time available for that bad activity to continue. And during that time, maybe some data has been exfiltrated. If you can't, it's not really preventing the event, it's killing it after the event. With Tetragon, we've implemented the ability to kill processes synchronously from within the kernel. So you can detect the event in the kernel, decide that it's malicious, and kill the event. So this is my last demo. I'm going to just apply a slightly different version of the same. So it's called etc. files kill. And this, the only difference between this and the policy I had before is that it's going to kill if there's a write to a file in the etc. directory. So let me run Tetragon again. I'm going to edit this file. And this time, I'm going to delete my extra line and try writing it. But I actually got killed. And let's just check, if we look at the file, if we got killed in time, the extra line should still be there. And there it is. So we can kill that event quickly enough to prevent bad activity from happening. So I think that this is a super exciting use of eBPF for security. We get all the advantages of eBPF instrumentation. We can load eBPF policies dynamically. They have no need to modify your applications in any way. You don't have to change any configuration. But we have this ability to provide amazing security forensics information and the option to actually block malicious activity. I hope that's given you just a bit of a flavor of why I think eBPF is so powerful and interesting. We've got a couple of books that we're giving away on the Isovalent stand I mentioned before. I'll be signing some of them later on. If you're interested in eBPF, there is a virtual event at the end of the month, 28th and 29th, called the eBPF Summit. It's a community event about eBPF. We've got some amazing talks lined up for that, so do come and join us for that. And with that, I hope that there will be a few questions.
Come with me to the center. Thank you, Liz. We have some questions, but we only have 2 minutes of time, and it's lunchtime. No. So I think we need to send people out quickly. Please, please, please help us and vote for the questions you think are most important and most interesting. We start with the first one. It already has 7 votes. Is there a performance impact at a syscall level if tracing with eBPF is active?
Yeah, this gets asked quite often. I mean, eBPF is incredibly efficient. And actually, there are a few, there have been evolutions in how we hook into syscalls that have become even more performant. The answer is you could write a pathological program that would have a serious impact on performance, but typically, no, there's not really going to be much in the way of discernible impact.
OK. Who controls which eBPF runs in kernel space? Can't it be used to hide rootkits?
Yeah, great question. Yeah, so with great power comes great responsibility. You have to treat eBPF like root access. If anybody can install eBPF programs into your system, yes, they could do malicious things. There are examples of eBPF-based rootkits. There are all sorts of malicious things you could do with eBPF. You can use eBPF to observe other eBPF programs, though. So it does become a bit of an arms race, but essentially, you do need to be privileged to install eBPF programs, treat it like root, be careful about where you get your eBPF programs from and what they're doing. Yeah.
Last question we do. How do you assess the risk from malware that uses eBPF, and how can I prevent this?
I feel like that's a similar question to the previous one. Using eBPF to detect eBPF is probably where we're at the moment. I mean, if you have got a rootkit, there's not going to be a lot you can do. But that applies to any rootkit. That's not new with eBPF.
Okay.
Okay.
Liz, where can you be found for the questions that are open?
I will probably grab some lunch, but I will be on the Isovalent booth probably most of the afternoon. So just come by, and in about an hour, I'll definitely be there. So yeah, come by and ask all your questions.
Thank you so much. This is for you.
Oh, wonderful. Thank you.